Hi students, today we are going to discuss a new topic, that is paraxial rays and paraxial approximation technique. Now let us see what are paraxial rays. Now I am going to tell you a fact which is quite unfamiliar to you. You might not have noted this fact till now. That is, if the incident rays are far from the principal axis, then they do not converge to a single point on the principal axis. What did I tell? If the incident rays are far from the principal axis, then they do not converge to a single point on the principal axis. Now to prove this, I have drawn the diagram here. Now this is a concave mirror drawn here, and this is the principal axis. This is the pole of this mirror, and this is the center of curvature. And actually this point F is representing the principal focus that you are familiar with. What is the principal focus? You have learnt in all your smaller classes that rays which are parallel to this principal axis will converge through the focus, Now this is a fact which is known to all of us. But what I told just now is, if the incident rays are far from the principal axis, incident rays principal axis il ninnu valare agalathilanengil aa rays ellam ഒരു പോയിന്റിലേക്ക്, അതായത് ഫോക്കസിലേക്ക് കൺവേർജ് ചെയ്യില്ല എന്നാണ്. That's what I have told now. So let us see how it is happening. Now these are parallel rays which are parallel to the principal axis. This black line, red line, blue line all represents light rays which are parallel to the principal axis. Now see the first incident ray, that is this black line. It is incident on the mirror at this point. Now I am drawing the normal to this surface, to this mirror at this point. How did I draw the normal? I drew a dotted line from C till this point. Okay, so the line joining the center to a point on the mirror, that is what I have actually drawn is the radius of curvature of this lens. Now the radius of curvature of the lens drawn to a particular point on the mirror gives the normal at that point. We know that a line drawn perpendicular to, this is a line drawn which is perpendicular to the tangent at this spherical surface. So it will naturally make an angle of 90 degree. That is, this line will be the normal to this surface at this point. Now I have drawn the incident ray. I have drawn the incident ray here, and that incident ray, this is the incident ray, and this is the reflected ray. Reflected ray. Now the reflected ray touches the principal axis at this particular point. The reflected ray is touching the principal axis at this particular point. Now consider the next ray. Now this ray is also quite far from the principal axis. The speciality of all these rays which I am going to discuss with you now is that all these rays are very far from the principal axis. Now consider the second ray. Now I have drawn the normal to that point here, and it is converging to some other point on the principal axis. The next ray here, it is converging to a third point on the principal axis. All these rays are converging to different points on the principal axis. Now this is a new information to us, that is, when the rays are very far away from the principal axis, then they do not converge to a single focus, or they do not converge to a single point. But we have learned in our earlier smaller classes that rays parallel to the principal axis converge through the focus, or they converge to a single point on the principal axis, which is called the focus. Now when is that fact applicable? എപ്പോഴാണ് നമ്മൾ ചെറിയ ക്ലാസ്സിൽ പഠിച്ച rays which are very close to the principal axis passes through the focus? When is that fact applicable? This fact is applicable only for rays which are very, very close to the principal axis. When the rays are, incident rays are very close to the principal axis, I have drawn here, see all these rays, they converge through the focus itself, a single point, as we have expected. So it is only the paraxial rays, these rays which are very close to the principal axis are called paraxial rays. So only the paraxial rays converge to a single point on the principal axis, or it is only the paraxial rays which converge to the focus. I hope what are paraxial rays is clear to all of you. Now what is the speciality of these paraxial rays? Now consider the rays which are very far from the principal axis. Now this is the angle of incidence for the first ray. This is the angle of incidence for the second ray. This is the angle of incidence for the third ray. If you measure these angles of incidence, what you find out is, as the ray comes closer and closer to the principal axis, the angle of incidence goes on decreasing. It becomes smaller. See, when you reached here for the paraxial rays, the angle of incidence is very, very, very small. So that is our next finding, that is for the paraxial rays the angle of incidence is nearly equal to 0. For paraxial rays the angle of incidence tends to 0. Okay, now what is the reason why I just told you, or I geometrically through this diagram I just represented that when the rays are far away they do not converge to a single point, and when the incident rays are very close to the principal axis, or when the incident rays are paraxial rays, they converge to a focus. I told you these facts verbally and I showed it diagrammatically. Now let us prove it mathematically. What is the reason for this? Now let us show the mathematics for this. For that we'll consider our next diagram. See, now I have taken a ray which is very far from my principal axis. This is my mirror. Sorry, I have forgotten to mark this non-reflecting surface. Okay, you can complete and consider it. Okay, so there is an incident ray like this which is far from my principal axis. So this is my principal axis with the pole here. This is the center of curvature. Now for this incident ray I have drawn the normal to the surface, that is this dotted line, and this is my reflected ray. So this is the angle of incidence, this is the angle of reflection. Since by laws of reflection both these angles must be equal, so I have represented them as cos I itself, both of them as I. Now I am going to find out the focal length in this case. Now this is the point Q where my ray has converged. Now what is the focal length here? Focal length is the distance between the pole and this point of convergence. So this is the focal length. So I have to calculate PQ. That's what I am going to do here. Now to find out PQ, I make these constructions. What I do is I drop a perpendicular from the point Q to this line CR, that is my normal. I drop a perpendicular from Q, that is the point of convergence here, to the line that is the normal, that is CR. Okay, now from this figure, if this is my angle of incidence I, if this is I, then my angle of reflection is also I, and if this is I, then this angle here will also be I. It is simple mathematics. Okay, how all these points become I think it's quite easy for you to recognize. These are two parallel rays, that is my incident ray and principal axis are two parallel rays. So if this is the transversal, so these are alternate interior angles. So if this is I, automatically this will be I. Now consider the triangles CQM and RQM. Now QM, this side is common. This angle here at M, both are 90 degree, and the angle at C and R, they are equal. So the two triangles are congruent. Triangle CQM and triangle RQM are congruent to each other. So what is CM here? CM is equal to MR, because the two triangles are congruent. CPCT, congruent corresponding parts of congruent triangles. Now what is CM and MR? CR is the radius of curvature, capital R. So CM and MR is equal to R by 2. It is half of the radius of curvature. Now what is CQ? What I want is PQ, that is the focal length. For that, first I calculate what is CQ. Now what is CQ? CQ is equal to, from triangle CQM, CQ is equal to CM by cos I. That is the simple trigonometric ratio. Now let us see what is PQ. Our focal length PQ is equal to, now see from the figure, PQ is equal to PC minus CQ. This is the total length. PC minus CQ will give you what is PQ. That is my focal length. That is what I wrote down here. That is PC minus CQ. PC is the total radius of curvature, R, the distance from the, you can see once again, it is the PC, that is R, the distance from the center of curvature to the surface of the mirror. So that is capital R, that is the radius of curvature. And what is CQ? CQ I have already found it out here, that is CM by cos I. What is CM? CM is again the radius of curvature itself, from the center to, that is this normal here. So what is CM? CM is half of the radius of curvature. This distance here is half of the radius of curvature. So what do I get here? When I substitute all these values, R minus CM is R by 2 and the cos I here. So focal length PQ is equal to R minus R by 2 by cos I. So what does this imply? Focal length depends on R. For a particular case, the radius of curvature, for a given mirror, the radius of curvature is a constant, 2 is a constant. So what varies? Focal length depends on the incident angle. So incident angle decides the focal length. But I told you here that as we come closer to your principal axis, when we consider rays which are very, very close to the principal axis, the angle of incidence becomes nearly equal to 0. Okay, so that is for the paraxial rays, it becomes 0. Whereas for these angles, these incident rays, when you go farther and farther away from the principal axis, the angle of incidence goes on increasing. So the rays converge to different points because the focal length is different. We found out here that focal length depends on the angle of incidence. But when we come towards the paraxial rays, I is nearly equal to 0. So what happens to our equation? PQ is equal to R minus R by 2 cos 0. Cos 0 is 1. So PQ equal to R by 2, which is the focal length. This is what you have been learning in your smaller classes. So till now, when you were learning about the formation of images in mirrors and lenses and all, we have been considering only the paraxial rays. We have been considering the image formation only due to the paraxial rays. Now, you will be feeling a doubt here. How can we limit our image formation to only paraxial rays? Now, mathematically we have approximated, we have considered only these rays, and we can prove that all the rays which are very close to the principal axis and they are parallel to the principal axis will converge to a single point. But what about the other rays? They will always be there. That means all these rays will come and they will converge at different points. The paraxial rays will converge to the focus. So but what will happen, because the rays are converging to different points, we get a blurred image and a spread out image. That is possible. But what we do is, we take only mirrors and lenses with very small apertures. For all practical purposes, we do not take such large mirrors or lenses. We take only mirrors having small aperture, so that only paraxial rays will be incident on it, so that our rule, that is rays which are parallel to the principal axis will converge to the focus, will remain valid. Okay, so we do not give an option for the other rays to come and fall on our principal axis, to be incident on the mirror and to be incident on the and to get reflected onto the principal axis. We take mirrors of very small aperture, so that only paraxial rays will come and fall on it. So I hope this is clear to you. Now what is these are paraxial rays which are very close to the very close to our principal axis and having angle of incidence nearly equal to 0. Now what is paraxial approximation technique? Now in paraxial approximation, we trace out the path of rays and image position on reflection and refraction from spherical surfaces. That is, by using this paraxial approximation technique, we can find out the image formation due to spherical surfaces. Suppose you are given a combination of mirrors or a combination of lenses, combination of different reflecting and refracting surfaces. Suppose you have to find out the position of the final image. We use only the paraxial approximation technique. So what comes under paraxial approximation technique? What are the approximations that we take place here? What we consider here? First, let us consider the refraction at a single spherical surface. So we are considering a spherical surface here, and this is a refracting surface. So there are two media here, one having refractive index N1, that is outside the spherical refracting surface, and the refracting surface, let it have a refractive index N2. Okay, now here let C be the center of curvature and P is the pole of this refracting surface. Now O is an object, a point object here, and this is our incident ray. Incident ray. This is the normal to the surface. How do we draw the normal to the surface? At this point, you just join that point to the center of curvature. You get the normal to that surface. Okay. And this is the incident ray and this is the refracted ray. Refraction is taking place here. This is a refracting surface. So this is the incident ray making an angle of incidence phi 1, and this is the refracted ray making an angle of refraction phi 2. Now what is paraxial approximation? Okay. Actually the point object will emit rays at all different angles, at different angles of incidence, very large angles of incidence also it will emit rays, that is rays which are very far away from the principal axis, and all of them will be brought to focus at different points. But we take only very small refracting surface having very small aperture, so that only paraxial rays need to be considered. Okay, for all paraxial rays, this phi 1, that is the angle of incidence, will be very small, nearly equal to 0. So that here we consider from the figure, phi 1 is my angle of incidence, phi 2 is the angle of refraction. I write down what is phi 1 and what is phi 2 in terms of different angles, combination of different angles. Now what is phi 1 equal to? To find out what is phi 1, I consider that this triangle here, this one, this triangle. I think it has become an utter mess. So I'll erase all these and let us draw it once again. This triangle here, this one, this side, and this side. So I am considering this triangle. Now this is the exterior angle of that triangle, this phi 1. So that exterior angle is equal to the sum of the interior opposite angles. So phi 1 is equal to alpha 1 plus beta. Okay, phi 1 exterior angle is equal to sum of the interior opposite angles, alpha 1 plus beta. Similarly, I try to find out what is alpha 2. But for phi 2, for that I consider a different triangle. I consider this triangle here. I think I should give a different color. Now the triangle that I consider here is this one. This side, and this side. Now for this triangle, beta is the exterior angle and phi 2 and alpha 2 are the interior angles. So beta must be equal to, that is exterior angle must be equal to what? The interior opposite angle, that is phi 2 plus alpha 2 must be equal to phi 2 plus alpha 2. But what we need is phi 2. This is our angle of refraction. So I rewrite this as phi 2 equal to beta minus alpha 2. In the first case I got phi 1 is equal to, that is angle of incidence equal to alpha 1 plus beta. And in the second case I got phi 2 is equal to beta minus alpha 2. Okay, using simple mathematics. So I think it's clear to all of you. I have written those two equations here. Phi 1 equal to beta plus alpha 1 and phi 2 equal to beta minus alpha 2. Now using paraxial approximation, I know all these angles are very, very small. So sin phi 1 can be, that is sine of, I am going to apply Snell's law here. So for that I want sin I by sin r. Sin I, angle of incidence is phi 1 and sin r, angle of refraction is phi 2. So sin phi 1 is equal to tan phi 1, which is nearly equal to phi 1 because the angles are very, very small. And so sin phi 1 I got it as phi 1. So sin phi 1 nearly equal to phi 1 equal to beta plus alpha 1. Now beta plus alpha 1 I am going to replace it with tan beta plus tan alpha 1. Tan beta plus tan alpha 1 because beta is equal to sin beta equal to tan beta, alpha is equal to sin alpha 1, tan alpha 1. You can write all these. So I have replaced beta and alpha 1 with tan beta and tan alpha 1. Now what is tan beta and tan alpha 1 from the figure? Now this is alpha 1. Tan alpha 1 must be equal to this height h from the principal axis to the point of incidence, that is h, and this is x, adjacent side, opposite side by adjacent side. So tan alpha 1 is equal to h by x and tan beta is equal to h by r. R is the radius of curvature, small r is the radius of curvature. Similarly for alpha 2, I replace it with tan alpha 2. Tan alpha 2 is h by y. So this will be needed for us. That's why I am telling again. So what is y? Y is, if I is the final image position, this is my incident ray, this is my refracted ray touches here. So this is the image position and O is my point object. So x is actually my object distance and y is actually my image distance. Okay, so by using x, r, y and h, I am going to replace all the trigonometric ratios. All trigonometric ratio ഞാൻ ഈ terms ഉപയോഗിച്ച് replace ചെയ്യണം. So sin phi 1 is equal to phi 1 equal to beta plus alpha 1, that is tan beta plus tan alpha 1 h by r plus h by x. Sin phi 2 equal to phi 2 beta minus alpha 2 tan beta minus tan alpha 2 h by r minus h by y. Now I substitute these relations in Snell's law. Sin phi 1 by sin phi 2 equal to n2 by n1. So n1 sin phi 1 equal to n2 sin phi 2. I just cross multiply, and in the place of sin phi 1, there's a it's a bit unclear, I'm sorry. Sin phi 1 and sin phi 2, I replace the ratios h by r plus h by x, h by r minus h by y. So when I rearrange, I get n2 by y plus n by n1 by x is equal to n2 minus n1 by r. Now n1, n2 are known to us, refractive indices of the medium and the lens. X is the object distance which you can measure. R is the radius of curvature of the lens which is known to you. From this we can determine what is y. Y is your image distance. Image distance can be, so the position of the image can be accurately found out by using paraxial approximation technique. Very easily you can find out by using Snell's law and paraxial approximation technique. That is why we have devised this method. It is used to determine the image position. But to get the accurate image position, you have to apply the sign convention. Now these sign conventions are all, I think it's familiar to you. That is, rays are always, we consider only the rays which are incident from the left of the reflecting or refracting surfaces. Distances, we consider the rays to be incident from the left, and all distances from the right of the pole. I'll show you a figure. With respect to this figure, all distances towards the right of the pole are taken positive, and all distances to the left of the pole are taken negative. We consider only rays to be incident from the left, and those rays from those distances at the right of the pole are positive, left of the pole are negative. So x is negative, r and y are positive. So if you replace it in our final equation that you got, then our equation becomes like this. Applying the sign convention and replacing x and y with our familiar u and v. So x becomes minus u, y becomes minus v, and small r becomes capital R. So this is our final equation. N2 by v minus N1 by u equal to N2 minus N1 by r. So this is the exact image point due to refraction at a spherical surface. And this equation is called the Gaussian formula for a single spherical surface, which this N2 by v minus N1 by u is equal to N2 minus N1 by r. So I hope whatever I have discussed today, what are paraxial rays, what is paraxial approximation technique, and all are very clear to all of you. If you have any doubts, please do contact. Thank you.